Anyway, we're covering thermoelasticity, where you do have differences in how materials expand relative to one another, and that can cause cracking in the different metals or the composite. And so the example I gave was a metal bonded to a composite, but is subjected to an environment in space that could be cold or hot, and each of those materials are bonded, are expanding at different rates. The second example I gave was a blisk, where you have in a rotor of a liquid rocket engine, the blisk is getting cold, the blades could be hot, that different expansion can cause cracking. So what I want to do today is cover the effects of thermal loads and what can that do. One of the questions I have for you is, what do you think happens when I say I took the cell phone here and I placed it here? And it was manufactured at room temperature, but I placed it here and heated it up. If I heated it up, what do you think happens to this cell phone? It's going to expand, right? It wants to expand, correct? There are materials, however, that defy the way things work, and you can design them that way, where if you heat them up, it will contract. So there's a lot of different ways to make that happen, to design materials that do that, particularly composites. We can do that. We can tailor the material so that it does something different than you will have expected with a normal material. So thermal stresses can cause structures to break. I gave you two examples, just practical examples for you to consider. What I want to remind you here is, I want to remind you that the strain was given by this relationship here. The strain is related to stress through this relationship here. So even if there's no stress in the structure, and I apply a thermal loading to a structure, is going to expand or contract. And so alpha here is called the coefficient of thermal expansion, and the coefficient of thermal expansion can be measured in a lab environment. There's multiple tests that can be done to measure that particular property. I'll not particularly cover it today, but there is a test, and the test is the E831 ASTM standard. Is able to then measure the rate at which the material expands as a function of temperature. As some materials, the alpha will also depend on temperature. So the coefficient of thermal expansion for a lot of the applications you will be working on could be constant across a range of temperature, but let me emphasize, there are materials where the coefficient of thermal expansion can also depend on temperature. Well, if you recall, strain is a measure of relative deflection. And so if I have no stress in the system, but I had a delta T and a strain shows up, that strain is showing up because of the delta T, the temperature that you're introducing into the system, times the coefficient of thermal expansion gives you the strain. One thing to really understand about these units, which I think is worth covering right now, is that alpha typically has units of length per temperature. So it's going to have those kinds of units. And so when you multiply alpha times delta temperature, then the temperature cancels out, and what you get is the units of strain, which is length divided by length. And I hope that is clear to you, what I'm talking about there. So it turns out that if I were to set everything to zero, all the stresses to zero, it turns out that this material here, this iPhone, for example, or Android, I have both, take your pick, so that I don't have enemies that way. You know, we have both. If I took both of these and subjected it to delta T, this is telling me, look at this, this is telling me that it's going to expand in all three directions. Alpha delta T, and alpha delta T. So it's going to uniformly expand in each of the three directions. That's what's telling us. But we're also making a fundamental assumption, and it's a good assumption, is that the shear strains are not affected by the delta T, by that thermal load I'm applying. And when I say thermal load, I'm talking about that delta T there. So yeah, so that's how these things work. There's 6 components of strains you can see here. And I can now, so I don't want you to lose sleep over the following thing I'm going to show you, but I can now write the strain-stress relationship so that it's written in terms of stress-strain relationship. So I can now invert the relationships so I can use them in this way. Now, am I going to ask you to memorize this one? No, I'm not going to ask you to memorize this one, but I think it is worth memorizing this one because it's very easy. I derived these equations using experiments in class that allowed us to derive these equations in a very easy way. And there is a question, so let me take that. The question is, why are the shear strains not expected by, affected by thermal? Let me clarify that a little bit. For an isotropic material, for metal, for example, that's isotropic. And let me explain what isotropic means, okay? Just to make sure you understand it. I have this big chunk of metal, say. I close my eyes, okay? I close my eyes and randomly I extract a little specimen out of the big chunk of metal. And then I close my eyes again and choose another piece of metal within that chunk of metal. Then I close my eyes again and choose another one. Those 3 are going to have very similar modulus in Poisson ratio. For materials like that, you don't see an effect of, you don't see things getting distorted because I only applied a thermal load. However, if you were, and that's an experimental observation, and it makes a lot of sense that when you apply a delta T, you expect things to expand or contract. However, that does not mean that a thermal load will produce a strain that causes shear. Let me give you an example that may make sense to you here, right now in this picture here. Let me try that. And I think it will make a lot of sense. So if I have, say, I'm going to make it up, okay? It's a big made up problem. Probably makes no sense. But I have this square here, this hollow tube, okay? And I decided for some reason to put in here a chunk of metal, like a tube, a bar, some bar. But actually, this could be a very practical problem. I actually know of an application of this. But say you have this situation, and I have this metal bar reinforcing this square hollow solid material here, okay? If I were to apply a delta T to this, do you agree that this bar wants to expand? But the rectangle, it doesn't know anything about delta T other than there might be something going on because I kind of feel it here and here. Somebody's pushing me, right? But I don't know why. This bar knows it's delta T. You're gonna get a lot of shear here on this material because you're distorting. You're gonna have it's gonna distort. Like if I were to predict how this gonna deform, I'm gonna predict it's gonna deform something like that. Agree? If that bar is kind of pushing out, so don't you think you're gonna get a lot of shear there? Potentially. I'm talking about when I'm showing these equations, I'm talking about if you just took a material that's unrestrained in free air, right? Just freestanding, and I applied a delta load. That's what will happen. But it doesn't mean that it won't produce a shear strain when it's embedded in something else or something like that. Is that making sense to you? Okay, great. And then I do have another question. That's an excellent question. Absolutely. So in orthotropic materials like composites, then you do have a difference in the coefficient of thermal expansion in each of the 3 directions. And I have a whole series on YouTube that teaches composite materials that you can watch, and I teach how to deal with the coefficient of thermal expansion in that case. But for this particular lecture, I feel that the right thing to do is just stick to isotropic materials, and then later on, you can take a composites course that covers how to deal with those more complicated problems. Great. And so I can invert these relationships to get the stress-strain relationship. Okay, I think we have a problem. This equation here, don't memorize this, but this equation here, I think you should put some effort to understand how it was derived, because I actually derived these equations using just logic. These equations are derived from logic. It doesn't require some mathematical derivation. It's just experiments, right? And I did some virtual experiments in class on how these coefficients can be derived. Now, this one is the inversion of that one. You have stress is related to strain according to these relationships. And you can see that alpha delta T showing up here, right there, in that last term. And the Poisson ratio is playing an influence there in these calculations. And so if I move forward then, what I want to do, I want to specialize this problem, this 3D, because in 3D we can probably solve a lot of different kinds of problems with this, probably fairly easily. In fact, we can actually even do one just quickly so you can see what it'll feel like to do this. But say I have this rectangle here, and this was the X, the Z, or well, let's call it the X, for example. This is the Y, and this is the CZ, for example. And I have that chunk of metal that I'm trying to figure out what's going on. You can actually use this fairly quickly to solve any problem. So for example, if I know that this is fixed, this boundary is fixed, the epsilon x, so say the x direction is fixed, and I apply a heat here, delta T. So let's look at what we do know. We know the modulus. So let me circle everything that I know. I know the modulus, I know the Poisson ratio, I know the delta T, and I know alpha. So in reality, I know all this stuff, I know all this stuff, and I know all this stuff. The only thing I don't know, according to this problem statement, is epsilon xx, epsilon yy, and epsilon zz. And if you notice, because I'm fixing this on this end and this end here, right? I'm fixing that bar. For this particular problem, you can quickly see that epsilon xx should be 0. Let me erase this to make it more clear. This right here. I did order a pen, so it should arrive soon. And that way we can use a pen to explain this. This is 0, right? We also have that on this boundary, the boundary surrounding this material, I'm not applying any stress. Is that correct? I'm not applying any stress. So you can set that equal to 0. There's no stresses on this one at that boundary. And then you can use these equations to solve for the unknowns fairly quickly, for the strains, for the stresses, and all that. So 3D is fairly easy to kind of visualize this, but why we don't apply this to problems that we can actually get a solution fairly quick for interesting problems, right? So the first, I'm going to cover disks, solid, annular, and then I'll move to a cylinder that's fairly long, solid, and then hollow again. So that's today's lecture. I'll apply the thermal stress concepts to that problem. Let's start with plane stress. A plane stress problem is one where the body of material is fairly thin, where through the thickness stresses cannot develop very much. And to remind you what that is, say I have this disk, and this is the z direction. If this thickness is relatively small, h, then sigma zz is, and sigma xz and sigma yz will be approximately equal to 0. Okay, so that's what you have there. That's what plane stress means. You have a fairly thin subject of material where you don't have the ability of these stresses to develop into high values through the thickness because it's so thin anyway. So that's what's going on there with that particular thing there. Now let's revise everything now that I'm converting this to a plane stress problem. I'm going to drop the z term, and you can see here I did that because the cylinder in polar coordinates has r, theta, and z as the coordinates. If you recall, what you really have for the coordinate system is radius, theta, and z. But I'm assuming that anything that has z is 0 because we're assuming plane stress. And as a consequence, I have simplified the strain stress relationships by setting sigma zz to 0. And so now everything simplifies to what you see here. Now here I put T, but delta T to me makes more sense. Every book does it differently. Some books just put T, some other books put delta T. I think delta T makes more sense because if you're manufacturing something at room temperature, that's your reference temperature. And that's the unstrained state, right? So you need some reference, right, to figure out what is strain is a relative measurement. So you need to understand, basically what I'm saying is delta T equals T, the final temperature and initial temperature. And what I'm stating is that the strain is 0 at a temperature of T, not. And so what I'm saying is it starts at a particular state, deformed, some state of coordinates of that system. But when you heat it up, it changes in shape or changes in size. Okay. So that's why I prefer doing delta T rather than T. A lot of books use they use T, but I prefer doing it the delta T approach. That's fine. It's fine. I just want to explain that to you. Now I can take these equations and invert them to get stress in terms of strain. Again, this is the radial stress. So that's the radial stress, sigma RR. And then this is the tangential stress, sigma theta theta. Okay. The modulus is E, the Poisson ratio is nu, and I'm applying a heat input of delta T. Although I'm using T in these notes to be consistent to the book. We can now recur back to the equilibrium equations. This is the equilibrium equations. We learned that already from the previous lecture. I keep using the same formulas. If we assume axisymmetry, where we don't have any dependence on theta, then the tangential deflection V is 0. So there's no deflection tangentially. All the deflections are radial. Finally, there's no dependencies on theta. So any derivatives on theta are 0. So therefore, you get these strain deflection relationships. And what I can do now, I can now plug in these relationships in here into the stress strain relationships. I know the strains. I can make the stresses to be a function of deflections, right? In the bottom equation there. When I do that, when I plug in this here into the constitutive law, what I get is, and then I plug this into the equilibrium equations, right? So that's step number 1. Plug in the strains into the constitutive law, then plug in those into the equilibrium equations as the next step. Let me clarify that. Then I get this equilibrium equation here, this differential equation, which is in terms of deflection alone. So what I'm studying here, let me remind you what I'm studying. I'm studying a thin disk that's subjected to thermal environments. And I want to see how that disk, how stresses get produced within that disk. That's what I'm studying. So so I plug in the strains into the stress-strain relationships, and then I plug in the stresses into the equilibrium equations, and the equilibrium equations turn into this differential equation, and the only unknown there is deflection. I know alpha, I know the Poisson ratio, and I have the term on the right turns out to be the derivative of temperature with respect to radius, meaning the temperature can vary across with the radius. What I can do now is to simply solve this differential equation by integrating it. So I did a little math trick. I did not invent this. So you can take this equation here and write a little bit differently. So it turns out that this right here is the same thing as this right here. It doesn't look like it, but it is. So it doesn't look like it, but it is. Just want to point that out. This right here is the same thing as that. It's a little trick. I invite you to try it at home. I'm not gonna do it here, but if you did it, I think you're going to get the same thing as I have above. So it's a little math trick, but it's very nice because now I can integrate this equation very easily. Integrate it once, and you can see here I integrated it. And then if you integrate it again, you get this deflection as as a function of two constants, C1 and C2. And you're integrating that from the A to R. Obviously, you have to have where to start with the integration limits of integration. Any questions so far on this particular point? Let me remind, the question was, what is U? I want to make sure that's clear. U is, let me draw it again, making sure we're all on the same page here. U is this deflection here, while this is V. And we're saying that V is 0, but U can be found. That's what I'm looking for. There's another question on here. Let me take that. The question for those on the line is, why I get a differential equation. And the answer is that the equilibrium equations in itself is a differential equation, partial differential equation. And so when I plug in the strain deflection relationships into the stress strain relationships, and then I plug that into the equilibrium equations, I get a differential equation. It's possible that the answer at the end gives you that the deflection is constant across the whole thing. It's possible, but it depends on the problem, right? And in this particular case, we can see it may not be constant across the whole plate. So this is a question I get, but I do, again, similar to the previous lecture where we covered shrinkage allowance and flywheels and other cases that we studied, we can see here that you end up with the C1 and C2 there, constants that I need to find. And how do I find constants in a differential equation? Boundary conditions. So I need to study the boundary condition of the problem and I have to figure that out. And I want to point out that for the general case that you're studying, once you find the deflections, the radial deflection, that can be plugged into the strain deflection relationship. And once you know the strains, you can get the stresses. And the stresses will look like this. It looks a little bit messy, but that's what you get. Again, once I know the solution for the differential equation, I can then plug in the radial deflection into the strain deflection relationship. And then those equations, which are in terms of strain now, in terms of deflection, can then be plugged in back into the constitutive law to get it all in terms of, basically you're finding stress as a function of temperature, if you see here in this equation. So I'm able, by solving for the deflection, I'm able to find the stresses as well. So in other words, anytime you know the deflection, you know strain, and if you know strain, you know stresses. How is that? Because if I know deflections, I know the strains through the strain deflection relationships, and then I know stresses from the stress strain relationship. That's how things are linked in. And so we've done that, but now how do I find C1 and C2? I want to be able to use the boundary conditions. I'll pause here for a second in case there are any thoughts, any pointers or questions you have. And if you don't have that, I'll move on then to the next slide here, where I repeat it. So I repeated this equation to the next slide because I know you're taking notes. So I repeated it here in the next slide, no worries. And what you see here, I'm going to study an annular disk. An annular disk that's subjected to thermal, delta T, a temperature in there, has, an annular disk is going to have these boundary conditions. The stress, the radial stress at R equals A, which is right here. I'm talking about this right here. Oh, right there. It's not letting me show you. Let me see if I can have the laser pointer work. Right there. R equals A. And R equals B is over here. At R equals A, that radial stress is 0 because it's a free surface and the radial component of stress is pointed radially. That's why that stress is 0. Outside of this body of material, you can see that it's also a radial stress of 0, right? Because there's no load acting to compress this. So therefore, the boundary conditions are this for the problem. And I'm ready now. All I have to do is notice that for this equation here, then one here at the top, sigma RR. I can impose these two boundary conditions, and that gives me two equations with two unknowns for which I can then solve for C1 and C2. I didn't do the derivation here because it's something you can do at home, but you get C1 and C2 there fairly easily. So I'm getting closer now to then finding the sigma RR, the radial stress. Once I know C1 and C2 from the boundary conditions for the radial stress, I can get the hoop stress as well, fairly straightforward. Because I know C1 and C2, I know what sigma theta is. Let me show you, I see, I want to make sure everybody's clear. R is a variable that goes from R equals A to R equals B. So I can plot that, right? E is a modulus, alpha is a coefficient of thermal expansion. These are material properties that are known, and Poisson ratio is known. So I know all this stuff, and I found C1 and C2. So all I have to do is plug it in, and now the hoop stress and radial stress all vary with respect to R. Question on here. Again, A and B are the radial point here in the inner radius, and then R equals B is the outer radius. Is that clear? Any questions so far on that? All right, let's do that. So, okay, let's go here. Let's look at the solid disk. The solid disk is an interesting problem because I'm going to use the same equations. There's no reason why I cannot use the same equations, right? The difference is the boundary conditions, right? Will you agree that the difference between this solid disk and the hollow disk is the boundary condition? The equations are the same, but the boundary conditions are different. So when I look at this example for the solid disk, what I realize is that the deflection at the center of that disk should be 0. Agreed? There should be any radial deflection in the center. It's in the center. So U is 0. But the problem is when you look at this equation, something similar happens to the other problems that we saw with the spinning disk. When R is 0, what happens to the deflection here? Goes to infinity. So therefore, you have to make C2 equals 0 so that doesn't blow up. Make sense? I'm not too worried about this 1 over R because that will potentially cancel with this R here, so I'm not worried about that. But this one here is kind of there, and you have to get rid of it because if you put R equals 0, that blows up. And we know that the deflection in the center has to be 0 when I apply delta T. That point here should not be moving radially. There's just no way. So that's that. We also know that the outer boundary at sigma at R equals B, that sigma RR is 0. So you can solve for C1. You know that C2 is 0. And so you're done. That's it. You solve for C1. And that's what you do there for that problem. Okay. So we're going to move on next to the plane strain. So again, I'll cover thermoelasticity. So this part B of the lecture today, I'll be covering how to apply it to a plane strain problem. What was really plane strain? Plane strain was a situation where you have a very long, maybe a long tube, right? And that I'm able to say that every cross section is very likely to behave like the next cross section. And if you can do that, you're able to simplify the problem further. So we're going to study that plane strain. Let me remind you what the strain stress relationships look like. But before we tackle this problem, let's consider a long cylinder that is constrained on both ends. So it's fully constrained on both ends. If the cylinder is constrained on both ends, doesn't that mean that epsilon ZZ is 0, right? Because let me write a picture here of what I mean. I have this long cylinder. Z goes this way. X goes this way. And Y goes that way. And what I'm saying is I'm going to fix this right here, and I'm going to fix it right here as well. Okay. Do you agree that if I'm keeping those ends fixed, there's no relative deflection of this surface to that surface? You agree? Doesn't that mean that this direction, the strain should be 0? because I'm keeping it fixed. Yeah. So that means I can use the same constitutive laws I had before, but I'm going to plug in instead the fact that epsilon zz is 0. I can impose that condition. And if I impose epsilon zz equal to 0 in this condition, it turns out that I can solve for the stress in that direction. You see that? I can solve it. If I solve for stress in that direction, I get nu times sigma r plus sigma theta minus alpha times E times T. That's the stress along the cylinder, right? Any questions on that? Yes. Your question is why it's called plane strain. It's called why this is classified as a plane strain. Number one, it's a long cylinder. And a long cylinder is very likely, if you take any random cross section, is going to look similar than the next cross section. That's number one. Number two, however, the ends are constrained. In this case, the ends are constrained, which means that I shouldn't expect a strain in the z direction, like I had shown before. And that's what makes a plane strain problem here. And then you can see here that I have this equation here, sigma zz, and I think everybody can agree that can plug in sigma zz into the first two equations of strain over here. Epsilon rr and epsilon theta theta have a sigma z in there. I can plug this into that equation, and when you do that, you get that the strains can be written in terms of sigma r and sigma theta alone. I'll pause there for a second. A good exam problem for those that could not make it today is this disk either being fixed in the outside boundary, which means that u is 0 at r equals 0, and I can get that C2 is 0. Sure, I got that one. But the other boundary is that u is 0 at r equals at the outer boundary, whatever this radius is. And so that gives you another boundary condition that you can use to solve for C1. So you have two unknowns and two equations now to solve for one of them. C2 is 0 for sure, because at r equals 0, obviously nothing's going on. C2 has to be 0 at r equals, because of r equals 0 blowing up here for the solid disk. It's not the case for the hollow disk, doesn't have this issue. But that could be problem number one, where the disk is getting fixed around the circumference, which means that u is 0 at r equals at that boundary, the radius at that boundary, which gives you the second constant that you're looking for. The second problem that could come up is, what if you have this disk rotating and spinning and it's getting hot? Well, don't I know the radial stresses and the hoop stresses for the thermal case? Don't I know them? I have the equations written here for you. So in the exam, if I was you, I'll copy the same equations, put a plus sign, calculate the spin stresses, and add them up. Because I told you the principle of superposition applies. You can study different cases and add them up. I can get fancy. I can apply in the exam, I can say, okay, it's spinning, but I also apply a pressure outside. And I apply a thermal load too. Well, then that's three cases. It's spinning, analyze that, right? The other one is, I apply outside pressure to this thing, and then I apply delta T, add them all up. Superposition applies if the stresses can be added linearly. Okay, so that problem is in fact, that's the problem I'm going to give you, because it's a good problem. Or I will not. Let's keep going. Okay, we got to this point for the long cylinder. I solve for epsilon zz. Sorry, I solve for sigma zz. And now I found this, and I plug that back into the first two equations, which gives me these two strains here, right? So now my strains are only in terms of sigma r and sigma theta. That's it. I'm able to solve one for the other. So now what I can do, following the similar procedure I showed before, I won't bore you with the details, but I can plug in the strains in here. I have now the stress, now I can invert the stresses out of this equation. You can invert this, so it's all in terms of strain. plug it into this equation to get a differential equation, so it's all in terms of u. Just like what I did before, I'm just not going to repeat it because it's the same thing over and over and over. But I'll repeat it one more time in case it didn't sink in. I want a differential equation in terms of radial deflection, u. So what I'll do, I'll plug in the strains into here, right? I'll solve for stresses because I have two equations. I can solve for stress, sigma r and sigma theta, in terms of deflection. Plug it into this differential equation, and I'll have everything in terms of deflection UR. So when I solve that differential equation, I get the equation here at the bottom that you see here. So this equation is different from the one we got for plane stress situation. It looks very similar. It looks very similar, but it's not the same. And I can compare them for you here. You can see that this is a 1 plus nu alpha divided by r for the plane stress situation. The radial deflection is 1 plus nu alpha divided by r, but this one here is 1 plus nu alpha divided by 1 minus nu times r. So a little bit different there. Poisson effect comes into play. It makes total sense to me. So now that I know the deflection, okay, so step back. I know the deflection, don't I? If I know the deflection, I know the strains in terms of the constants. If I know the strains, I can plug it in here and solve for stresses, which I didn't give it to you here, but you can solve for stresses. And then when you solve for stresses, one of the stresses you get is this one. Radial stress is this one. When you solve for radial stress. And then so once I find sigma r, I'm ready because I can find sigma theta. And I can find sigma theta from this very equation here, the equilibrium equation. I know sigma r, plug it in here. I know sigma r, plug it in here. Solve for sigma theta. That's how you find sigma theta. I won't even go into the details on how to find that because that's a plug and play. Sigma z, I already gave you the formula for sigma z. It was over here in the back here. Sigma z is that. I found sigma z by solving for epsilon z equals 0 from this equation. That's how I found sigma z. So just plug it in there. And when I do, I get this equation here for sigma z. We'll just keep moving here then. No questions on that. Awesome. Let's look at the problem of a solid cylinder. So it's a solid cylinder with a fixed end. Let's apply the boundary conditions now. I haven't done that yet. So the boundary conditions for a solid cylinder, what are they? Is u equals 0 at r equals 0, right? Because at the center of the solid disk or solid cylinder, the center of that cannot be moving around. So therefore, it's the same situation where C2 goes away. Same situation. It's the same situation also for the solid cylinder that sigma r is 0 at the outer boundary. So I plug in what r is, which is b at that boundary if the outer radius is b. And when you do that, you're able to find C1. So once you find deflection, because you have the deflection in terms of C1 here, you can see here at the bottom, I found C1. Once I know C1, I know everything because I know the deflection in terms of C1. I know everything there. Once I know deflections, I know strains. Once I know strains, I know stresses. So they're all connected. Once you know one thing, you know everything else through this relationship you see here. Yeah, so these are the equations at the end that you get. When you substitute C1 into the stress equations, you get these formulas here. And yeah, and this is the stress equation for the axial direction with C1 already plugged in. Very cool. I think it's a very straightforward problem. You can see that everything turns out very nice. For example, if it's a solid material that's a cylinder, at r equals b, you can see that this term goes away. It makes sense because sigma r should be 0 at the boundary. So that makes total sense. We can try other things like plotting the temperature. What is the temperature say what is the stress in the center. We can probably solve for that too. You can do every combination you want, and see what will happen, just out of curiosity. Okay, so that's what we get. Any questions? Do you agree? Do you agree that if you're studying a heat conduction problem where you apply temperature, say to an iPhone, so say it's getting hot here where you're putting the charger, do you agree that temperature could vary across? So it's possible that I can give you a temperature distribution that's not constant. So delta T I can tell you, hey, in the exam, that'll be problem number 4, actually, that the delta T that I'm applying can vary across the bar. Tell me what the stresses are. This should be able to account for that, right? Because then I can give you the temperature distribution as a function of radius, and you should be able to plug that in to solve for what the stress is. It doesn't matter because if say temperature was linear with radius, right? Then I'll give you a function, right? So I'll say this, for example. This is what I could do, right? I could say, okay, this is what I have. This is what I have. I have a delta T that's equal, and then that's equal to, is going to vary with radius. I could say that. You plug that in here, and that's it. That makes sense because sigma theta is going to depend on that now. That's what that's saying. So yeah, it's possible to look at different scenarios with the same formula. Hopefully that's clear, that example problem. Yeah, the more questions you guys ask, the more examples I have that I can use for the exam. So I appreciate that. I'm just kidding. I think they're great questions. Any other things that come to your mind? I also did not say it will be an exam. I say it could be an exam. So you don't know if I'm bluffing or what I'm saying is going to be true. All you know is that you need to know the stuff. Okay? Do you need to memorize formulas? We don't want to memorize formulas. I don't memorize formulas. Do you think I memorize these formulas? If I were to design a disk that's under heating conditions, will I memorize this formula? No. What will I do instead? Understand what the equation is saying and apply it. That's what I'll do. But you have to understand the problem statement. You have to understand the boundary conditions. If there's one thing here that you notice that we really have to get right, is the boundary conditions. If you don't understand what to do with the boundary conditions, the solution will be wrong. There is a question here that says, what order do you use superposition in? So you can add the stresses in any order you want, no problem. That's the first question that I was asked. Can I add the spin plus thermal plus pressure? Yeah. Can I add it? So spin plus pressure plus something else? Yeah. You can change the order. It's adding up. Please ask your question. All the equations are linearly additive, so you can superimpose them. Only if they behave linear in real life. If they start to have plastic deformation due to one condition, adding them like this doesn't make a lot of sense. But in real life, do you want to really design something that goes plastic for one of the conditions? Yes, that happens. Do I want to have that? I don't want to have that, but some designs force you to have that. Let me give you an example. A cooling channel in a rocket engine. The wall of the cooling channel has to be thin. Otherwise, how you conduct any heat from the fuel that's hot to the fuel that's inside the cooling channel. The purpose of the cooling channel is to cool stuff. But yet I have a temperature outside of 5,000 degrees from the rocket combustions, right? Inside the tube, I have a temperature that's lower that's trying to cool the channel. But if I make it too thick, then it's not conductive anymore. So there are some designs that push you in that way. Will I use these equations? No. I'll construct a finite element model, something that's quick and I can actually analyze it with finite element model. These equations are great for quick sizing, but I will not recommend them for very complex situations. That's where I will use finite elements, for example. Does that make sense to you? Yeah? So why would I move to an example where you have free ends? For the free end, so now I have a long cylinder, a very long cylinder, but the ends are free. So what does that mean? If the ends are free, it means that the summation forces in the z direction are 0. So it turns out that you can study the situation. Basically, you can do a summation forces in the z direction. So there must be some sort of stress acting on the ends and somehow that makes it free, because otherwise, why will be free end? So you can then use the fact, so this equation that you will use, this is at the boundary, so that's at this boundary, this term, while this term is somewhere in the inside of that boundary. In this case, it's easy because you already know sigma z from these equations here that I found, sigma z there. You plug it into this equation, sigma z, and that gives you the stress that you need to apply so that the cylinder behaves like if it was in free ends. So that's how you look at this problem. It's not a very practical problem, in my opinion. I think it could come up in real life. Let me think how. But it is a problem that we could study. I won't particularly give a problem on this in the exam necessarily. I'll have to think of an application that makes sense for this one. So let me explain how this came about. So a little more. So this term right here, right? That term right there is just if I have a radius of b, right? What is the area of that? That's pi b squared, correct? So that times the stress that's superimposed is a fake stress you're superimposing to get the free stress to go away. So that'll give you a that term right there. And then for this term, the way you want to look at that, and in my opinion, the way you will do this is you draw a concentric circle. I think you've seen this before, no? How to calculate the area for something like this. This perimeter is 2 pi r, and this distance is dr. That's the area of that. And then sigma times sigma z, and integrated through the thickness 0 to b, gives you the full disk area, right? So that gives you that stress. And you know sigma z. We know sigma z already. So sigma z is known because we solved it earlier. I don't know if you recall. I can remind you. This is a sigma r we got. See that? So I know sigma z. I know this constant. So I know what stress needs to be superimposed to be able to get that free ends free. So it's like a magic trick, using superposition basically to eliminate those stresses that are occurring. No problem. Absolutely. Go ahead. Okay. You can also get then the total stress. You can get the total stress in the z direction because you found we found this stress here with the fixed ends. We're not using that formula, right? But because that was for the fixed ends. But here, I have this equation for sigma z that I had earlier. I can plug it in here to get S naught. And then you can then solve for sigma z total because you have two equations here. You have this equation and this equation. So two equations, this equation gives you two equations. So you can solve for C1 and C2. Sorry, just for C1 and S naught. So you can solve for those. So again, this equation and this equation. That gives you because you don't know what stress you need to apply uniformly to get it to cancel out. So S naught is that unknown, and then C1 is the other unknown for the free end case, right? So I need to figure out a way of solving for that, so I can use this equation in combination with this equation to get the total value. So that's what I did. I found sigma Z total. Once you know that stress across the Z direction, you can then find the sigma, the radial stress, the hoop stress, and the deflections in a very simple way. The other special case that's typically studied is a hollow cylinder with fixed ends. The hollow cylinder with the fixed ends has an inner radius of R equals A, outer radius of R equals B. Again, it's the same formula I had before. Remember, for the plane strain condition with the 1 minus nu at the bottom? You can say it's the same formula, but you're going to impose the stress R equals A and R equals B to be 0. And then you can then solve for C1 and C2. So same stuff we did before. It's not changing. And then you can find sigma R and sigma theta and sigma Z in a straightforward manner. Okay. So again, you can see here that these are the stresses for the hollow cylinder case. I can also keep going now with the special case of free ends. However, I'll stop there because I don't think I'll cover this case necessarily. I'm flashing it here for you to know, but I think to me matters most that you understand the concepts on how this is applied in a general way for different boundary conditions. What I want to do now is to end it right here at this point in time.